Hello friends and welcome to today's Science Knowledge Base video. First of all, I would like to say a big thank you to those of you that subscribed. If you haven't already done so, click the subscribe button and the bell icon so you know every time I upload a new video. If you want me to go over any particular science topic, write it in the comment section below. Let's begin with today's video. Today I will be telling you about atoms and elements. There is no possible way to physically look inside an atom, but there is enough evidence from experiments for us to visualize a working model of the atom. Atoms have three subatomic particles: protons, neutrons, and electrons. The nucleus of the atom consists of protons and neutrons. These subatomic particles are the ones with mass of 1 unit each. Neutrons have no charge, and each proton has a charge of +1. Electrons, on the other hand, orbit around the nucleus. They have a charge of -1, so they have an equal and opposite charge to protons. However, electrons have next to no mass. Electrons are actually what interact for chemical reactions to occur. The nucleus can be described by the atomic number known as Z and the mass number known as A. The atomic number indicates the number of protons in the nucleus, so for helium that's 2. The mass number indicates the number of protons and neutrons in the nucleus, so for helium that's 4. That's why we can get the following equation: mass number A is equal to atomic number Z plus number of neutrons N. Bohr's theory describing the emission spectrum of hydrogen explained it in terms of energy levels, which was simple because hydrogen only has 1 electron. I will cover Bohr's theory in another video. For atoms that have more than 1 electron, we talk about electron shells rather than energy levels, and we refer to each shell by a quantum number n. The first shell, n is equal to 1, holds up to 2 electrons. The second and third shells, respectively, n is equal to 2 and n is equal to 3, hold up to 8 electrons. N is equal to 3 actually has the capacity to hold up to 18 electrons, but I've said 8 electrons for a reason, because things start getting strange after calcium in the periodic table. I will get on to electron subshells and atomic orbitals in a bit, which may make it better to explain this. The fourth and fifth shells, respectively, n is equal to 4 and n is equal to 5, hold up to 18 electrons, and the sixth and seventh shells, respectively, n is equal to 6 and n is equal to 7, hold up to 32 electrons. This diagram shows an illustration for the element hassium, which has an atomic number of 108 and 7 electron shells, just so that you can get a visual image of what I was talking about. The electron shells themselves are split into subshells. This lovely table here shows the first 4 electron shell quantum numbers and their electron subshells, and the number of electrons each electron subshell holds, and therefore the total number of electrons in each electron shell. Let me go through the n is equal to 4 shell. So n is equal to 4 has the s subshell, which holds up to 2 electrons, the p subshell, which holds up to 6 electrons, the d subshell, which holds up to 10 electrons, and the f subshell, which holds up to 14 electrons. And this means that n is equal to 4 has the capacity to hold 32 electrons. Each electron subshell is associated with a certain energy level, which is shown in this diagram. You will notice that there is an overlap in energy between n is equal to 3 and n is equal to 4. This basically means the 4s subshell from n is equal to 4 will fill before the 3d subshell from n is equal to 3. This is one of the many examples of overlaps. This diagram on the left is just a continuation of the previous diagram. So one way to illustrate the order in which electron subshells fill is this diagram on the right, and the arrows show the order in which the subshells fill. Even the subshells are further divided into atomic orbitals. Each electron in each orbital can only be found in a specific area in the atom. This diagram shows the shapes of the orbitals. So starting from the first row, the s subshell has one s orbital. The second row, the p subshell has 3 p orbitals. The third row, the d subshell has 5 d orbitals. And the fourth and fifth rows, the f subshell has 7 f orbitals. Each atomic orbital holds 2 electrons that will spin in opposite directions as a pair in that specific orbital. An electron with a clockwise spin is represented with an upwards arrow, and an electron with an anti-clockwise spin is represented with a downwards arrow. The electron pair is written like this, and the box represents the orbital, and in this case, that's the 2s orbital. Now, let me tell you what electron configurations look like, first by using the example of hydrogen, which basically has n is equal to 1. This is what the electron configuration for hydrogen would look like. The first 1 stands for the electron shell, n is equal to 1. The s stands for the s subshell, and the one raised after the s stands for the number of electrons in the s subshell. Now I'll go for a more complicated electron configuration. I'll use the example of calcium, since I said things get strange after calcium earlier on. So first we identify the number of electrons in the atom, which is 20 for calcium. It's the same as the number of protons. Next, it's important to remember that the lower energy shells and subshells fill first. So this is what we have so far. The 4s subshell fills before the 3d subshell. So the 4s gets filled, and then there's 1 electron left for the 3d. So that gives us this electron configuration for calcium. Moving on. Isotopes are atoms that belong to the same element, but with different mass numbers. They have the same number of protons, but a different number of neutrons. Most elements naturally have multiple isotopes, and the relative atomic mass is an average of the isotopic masses, acknowledging each isotope's abundance. This equation can be used to calculate the relative atomic mass. So let me give you an example. If the question says, calculate the average atomic mass of chlorine if its abundance in nature is as follows: 75.77% 35 chlorine and 24.23% 37 chlorine. If you substitute that into the equation, you get 35.48, which would be the relative atomic mass or average atomic mass. Next, we have a strange thing that doesn't actually happen naturally on Earth. In nuclear fusion, lighter nuclei of 2 atoms fuse together to form a heavier nucleus, hence forming a new element. This diagram shows 2 isotopes of hydrogen fusing together to form helium. Deuterium and tritium are the 2 isotopes of hydrogen, and you can see the reaction releases energy and a neutron. So needless to say, fusion reactions release a lot of energy. And the reason why I say this can't happen naturally on Earth is because of the Earth's temperature. There is a strong repulsion between the protons in the nucleus between atoms, and a lot of energy is needed to overcome this repulsion. And this can be provided by extremely high temperatures, such as in the sun and in stars, where there is enough energy for the nuclei to collide with each other at a high enough speed to overcome this repulsion. Here are the references for this video. Thank you for watching. Science Knowledge Base now has an Instagram page and a Twitter page, both of which you can follow for fascinating facts, silly jokes, and news. And finally, if you liked the video, don't forget to hit the like button, and I would love to hear your thoughts in the comment section below.